So we'll go ahead and get started. The other folks sort of trickle in, but it's certainly my pleasure to introduce Dr. Courtney McCracken. She's the director of the Pediatric Biostatistics Core out of Eggleston. She received her Bachelor of Science in Math from the University of Georgia in 2006, and then both her Master's and PhD in Biostatistics from the Medical College of Georgia in 2010 and 2012. And she's my wife, so be nice to her.
Well, I wanted to thank you guys for inviting me to come here and talk today. At first, I was kind of perplexed about what would be something interesting to talk about with you guys, and so what I thought would be most applicable and interesting are sort of two different topics. One is just statistical mistakes that we see all the time in the literature that I think can be very, very easily avoided. And then also talking about one particular method for analyzing data from non-randomized designs. And then I will illustrate an example that we've actually done in neurosurgery related to that example. So my disclosures, I don't have any, but several residents have traded wine for statistical consultations. So you may ask, why am I giving grand rounds today? Well, the number one reason is that my husband pressured me to come here today to give grand rounds. I do review for neurosurgery, so I've had an opportunity to review a lot of publications in the neurosciences. I have over 60 co-authored publications in peer-reviewed journals. And since I started at Emory, I've worked on over 500 clinical research projects. Now, granted, they're in pediatrics, but the flavor and the design and statistical issues are common across any medical discipline. I've seen several resident projects in this department, and I've even worked on a few. And several of you have called to ask me questions about appropriate statistical tests. So obviously that means that you care a lot about statistics and you're very interested in this talk today. So my outline of my talk, I'm just going to sort of go into the evolution of a statistician, specifically in medical research. I'm going to give you my top 10 reasons or common statistical mistakes that you can avoid, a quick review of non-randomized designs, and then I'm going to be talking about propensity scoring as a method for non-randomized designs. So the evolution of the statistician. There's been a lot of papers out there talking about, studies published in peer-reviewed medical journals may not always be 100% correct. And again, a statistic saying 30 to 70%, that's a wide range. But there are serious statistical errors that can skew the interpretation of results in medical research. And approximately half of the manuscripts that I review for neurosurgery contain very major statistical errors. So there was an article back in 1994 by a guy named Altman. He's a British statistician. And he basically published this paper called The Scandal of Poor Medical Research. And it kind of opened the door for people to see why there's so many issues about statistics in medicine and why we really need to involve statisticians in the peer review process. So the question that he posed in his article, which I thought was very interesting, was basically saying, what would you think about a doctor who uses the wrong treatment, either willfully or through ignorance, or who uses the right treatment incorrectly? So I ask you guys, what would you think about a doctor that did that? Bad doctor, right? So most people would argue that the behavior is unprofessional, unethical, and unacceptable, right? So then in that same article, we pose another question. So then what do you think about a researcher who uses the wrong techniques, again, either willfully or in ignorance, uses the right techniques incorrectly, misinterprets their results, reports their results selectively, cites literature selectively, or draws unjustified conclusions? Now, what do you say about that?
Mainstream media.
Well, you should be appalled. However, numerous studies in the medical literature in both general and specialty journals have shown all these things happen. So, we hold our doctors to a very high standard, but then we're not holding our research to the same standard. And that research is then being interpreted by our physicians and researchers to make clinical decisions. So it's been about 20 years since Altman wrote this article, and Now more journals are actually incorporating statisticians in the review process. Some journals have a statistician review every single paper. Other journals allow the authors to select whether or not they think a statistician should review the paper. There's also been different guidelines about how to standardize how we report studies, especially from randomized clinical trials and meta-analysis. I'm sure you guys are familiar with the PRISM and the consort guidelines. And then aside from that, statisticians are becoming this new quote-unquote sexy job. Google's chief economist called statisticians the new sexy job. And actually the number of statisticians growing in the workforce is rapidly growing. So why does that make me want to talk about common statistical mistakes? Well, because statisticians are being involved in the review process, these types of mistakes are being picked up more and more and more, and it's likely that a statistician is going to review your paper, and so if you can avoid these mistakes on the front end, then the likelihood that you would have to get another review, at least by a statistician, should be low. So, number one I want to talk about is failing to graph data and calculate basic descriptive statistics before analyzing your data. So does anyone know what a descriptive statistic is? Yes? Range, yes, that is one. A mean, a standard deviation. So what happens is we fail to assess our data for illogical values and or outliers. What happens, and I actually just finished reviewing a paper a couple days ago, that they had this outlier in their data, and they went back and forth between, should we include the outlier, should we not include the outlier? Well, at the end of the day, if it's a real value, then you probably should be including it. You can't just throw out data because it seems extreme. So one of the things that you can obviously tell when there's outliers in your data is that your standard deviation appears very, very large relative to the magnitude of your mean. So there's a very, very easy solution for handling outliers or even detecting them. Graph and explore your data first. I can't stress this enough. So many people just jump into their data, start doing t-tests, things like that. They don't even take the time to actually graph their data and look at it before they start to do any real analysis. You can also perform a sensitivity analysis with and without the outlier to see how it influences your results. But sort of the most robust way of handling it is to actually use methods that are not easily influenced by outliers. Report things like median and interquartile range instead of the mean. Which brings me to my next point, is using the wrong descriptive statistics. So what do you think are the most common descriptive statistics out there? Yes, a t-test is a test, but really the mean and the standard deviation, right? And surprisingly, the mean and the standard deviation are the number one and number two most incorrectly reported statistic. And why is that? Well, the mean and the standard deviation only represent measures of central tendency and spread when you have a nice bell-shaped curve. Most biological data does not follow this nice bell-shaped distribution. So again, the solution is easy. Graph your data to assess normality. Compare the mean and the median. If they're way off from each other, chances are your data are not normally distributed and you should be reporting the median. So what if I wanted to talk about, looking at some ways to describe data? So here we have PGY6 golf scores compared to PGY2. So this is the mean and the standard deviation, and here's the median. So the median is relatively close to the mean, and the standard deviation is relatively small relative to the magnitude of the mean. So here I would argue that the mean is well representative of the center of the data. But what if we wanted to look at the number of post-operative wound DBS battery changes, wound infections, implying by course PGY2 rotation? Well, here, the mean is quite high, and the standard deviation relative to the mean is quite large. So maybe this is not the right descriptive statistic. When we actually look at the median, we see that there were very few post-operative infections for Mike Moore.
This is clearly an example of making up data.
Yes. What about the number of bed bugs found in Grady call rooms compared to Emory call rooms? So we can see here that the standard deviation is quite large in this group, and again, maybe we don't want to report the mean. Oops, let's see. Oh, there we go. But in reality here, there's lots of variables that are used in practice that are not normally distributed. Length of stay is by far the most common variable not normally distributed. Most of the people will stay a reasonable amount of time, and then you've got those people that seem to stay forever. And what happens is it skews your distribution. So a vast majority of your data is sitting right here, but then you have all these outliers out here that are going to cause your mean value to go up. Cost is another thing. ICH volume can be not normally distributed, duration of follow-up, and of course lab values. So I want to illustrate two papers that I pulled out of neurosurgery. One was just looking at postoperative fever discharge guidelines, and they wanted to look at how that affected hospital charges in spine surgery. So I just pulled out their table 5 and showing you here that they're looking at patients with ACDF, no postoperative fever compared to postoperative fever, and you can see that they presented the mean and the standard deviation for both cost and length of stay. Now notice how large this standard deviation is relative to the mean. It's likely because there's outliers in the data. So again, this is probably not the correct statistic to be using here. But then there's another paper that looked at the effect of coiling versus clipping of ruptured and unruptured aneurysms on length of stay, cost, and a bunch of other stuff. They hypothesized that coiling would result in shorter lengths of hospitalization compared to clipping in patients with unruptured aneurysms. So you may think, oh, look, they presented mean and standard deviation. No, you have to pay attention. They actually presented the median and the interquartile range, which would be the correct measures of central tendency when you have skewed data. Okay, so the next one. Using the wrong statistical procedure in analyzing your data. This happens quite frequently. People will use a two-sample independent t-test when you have paired data. You'll use a two-sample t-test when the data are non-normally distributed. Or you'll use chi-square test when cell counts are low. My favorite example of some fellows or residents calling me, both Brian Howard and Jason Chu called and said, hey, I use a Fisher's exact test. Do you think that's right? And I was actually really proud of them that they recognized that. But this happens quite frequently. People don't pay attention to the assumptions, and as a result, their estimates and their outcomes may be skewed. So again, the solution, check your data. I can't stress enough how just plotting your data should solve a lot of your problems. Obviously, assess whether you have independent or paired data, and then make sure that you use exact tests when cell counts are small and frequency tables. So let's just illustrate an example of what happens when you use the wrong statistical procedure. So in fairness, I randomly generated numbers from hypothetical PGY3 and PGY4 board scores. I only manipulated one person's score for the illustration of my example. So in this type of scenario, this is a paired data, right? You have two measurements taken from the same person. So the first measurement is their third-year score, the fourth measurement is their fourth-year score. We expect a degree of correlation to happen, right? That how you answer or respond on your third year, you hope that correlates somewhat with how you do your fourth year. So let's look at the data. Just running some basic descriptive statistics, we basically have the mean and the standard deviation here and the median. So you'll note that the mean and the mean and the median are quite similar in most of these cases. But notice here, despite the mean and the median being similar, there's a large standard deviation in the difference between the 2 years. And it's likely because of that outlier. So when I actually just do a quick plot of the data, the solid blue line represents what a normal distribution would look like, and the dashed blue line represents sort of what the real distribution is. So we tell ourselves, hey, things don't look that bad. There's definitely some skewness to this data, and that there's an outlier down here, but again, it's not bad. The problem is we have only 12 patients or residents here. So given the large outlier and the fact that our sample size is small, we really can't assume normality. And so I think that that's really important to understand that when you have a small sample size, just because you think your data is normal, can you really even talk about assessing normality when you only have less than 30 people? So in this case, a non-parametric test would be the most appropriate. So we look at the difference, and again, we see this huge outlier. I don't know how this idiot is in the program, but what do? So raise your hand if you think we should use a two-sample t-test. Okay, good. You're listening. No, first of all, you shouldn't use a two-sample t-test because your data are paired. So that test assumes independence. How many of you think we should use a paired t-test? Mike's kind of smiling back there. You have no idea, right? Okay. So a paired t-test, you get a p-value of 0.054. So it's not statistically significant. How many of you think we should use a Wilcoxon sign rank test? Okay, some people raised their hand. How many of you know what a Wilcoxon sign rank test is? Yeah, non-parametric paired t-test, okay? When you do that, your p-value is 0.027. So you may think, oh, well, non-parametric methods are typically less powerful than t-test, parametric methods. But actually, if your data is non-normally distributed, this is going to be the most powerful method to use, especially in the presence of outliers, because those outliers will increase your standard deviation and make it harder to detect differences. Okay, so the next one.
Yeah, just point
Yeah.
out that there's in my particular area, there's a high-profile paper in the New England Journal of Medicine, which very small numbers they used. They did not use non-parametric tests. And in that case, the use of a standard assuming normality test generated a significant result that led to the paper being published. When those people that actually know the details of the test know it's a non-parametric test, it's actually very skewed. There are people that, it was a DBS from memory, there are people that respond sort of, they get the test and they can do it better or worse, and then there are some people that just do not get the test no matter what. So the data is not parametric, and when you do the appropriate statistical test, the result completely disappears. And this made it through the New England Journal of Medicine statistical review.
They're not all good, so. So the next point I want to bring up is about reporting measurements with unnecessary precision. So a lot of times, we report out way too many decimal places. So again, this is just sort of a nuance and kind of a pet peeve of mine, but really, like, what is a 4/100th of a year? It means nothing. My favorite is when we report p-values, right? So, like, what is the difference between these three p-values? This must be really significant. And in fact, I do a journal club for Pediatric ICU, and one of the papers we reviewed last week had this. Again, I just started laughing because, I don't even know what this means. So, I think neurosurgery actually does a pretty good job of how you report your p-values. But in general, if it's not significant, 2 digits is fine. If it's significant, 3 digits is fine. And you should never report anything less than 0.001. Just less than 0.001. That's all you need to do. So this next point I want to bring up is failing to...
Just
Go ahead.
following up on that, so the term highly significant means nothing, right?
I mean, I'll get into that. You have to realize that a p-value is nothing more than a function of the effect size and the sample size. So you could have the exact same effect size, but because your N is so large, it's going to drive that p-value way down, when it doesn't make a difference.
People use it as a measure of robustness. How big the difference is.
Right. So here is the next one I want to talk about, which is failing to report a confidence interval as well as the p-value. I think a lot of journals are moving towards this. In fact, some journals are moving away from even allowing you to report p-values. And the reason is that people get so fixated on this less than 0.05 thing that they completely lose the clinical significance, and they're willing to hang their hat on anything less than 0.05. And so all a p-value does is tell you something statistically significant, right? So this is my favorite interpretation, just what Dr. Gross brought up. Highly significant, right? Oh crap, let's redo our calculations. Maybe there's an outlier in there. On the edge. And then my favorite is, significant at the 0.1 level. There's a trend towards statistical significance. So confidence intervals tell you what the population value might be and aid in determining the clinical relevance. P-value doesn't do anything for you. So if I tell you that this is how you reported the results, the effect of the drug was statistically significant, what kind of conclusions can you draw from that?
It's not likely. It's more likely to be right than wrong.
Right.
And 95%.
Sure. Right. Use less than 0.05, but I have no idea what the effect size is. So it doesn't tell me whether what the effect size is, whether the effect is clinically important, or how statistically significant is the effect. So some readers interpret statistically significant in the case to mean that the study supports the use of the drug. It's not the case. Okay, let's add a little more information. The effect of the drug on lowering diastolic blood pressure was statistically significant. So here, again, we know what direction the effect size is going in. It lowered diastolic blood pressure, but again, we don't know what the clinical importance is. A p less than 0.05 can mean 0.049, and I argue that a p equal to 0.049 is no different than a p equal to 0.051. So again, this is not statistically significant. This is statistically significant, but they're really not that different. So now we give a little more information. The mean diastolic blood pressure of the treatment group dropped from 110 to 92, p equals 0.02. This is the most common way people report results in the literature. So we have the pre-test and the post-test values, but we don't know the difference. The average drop is assumed to be 18 because the difference between these two values is 18, but that's not actually true necessarily. We don't know what the mean difference for the group was. And without a 95% confidence interval, we don't know the precision of the estimate, and we don't even know what the true range could actually be for that value. Now I give you the last sentence. The drug lowered diastolic blood pressure by a mean of 18 from 110 to 92, and a 95% confidence interval from 2 to 34. So now this tells me that the true mean difference is likely to range between 2 and 34. So someone say 34, well, that's a great drop in blood pressure, but 2, that would mean absolutely nothing. So although the mean blood pressure in the study was statistically significant, the expected difference potentially in other studies may not be clinically important because it could be as low as 2. Fishing. How many of you guys like to go fishing? How many of you guys like to fish for data? So I always tell first-year fellows in pediatrics when I'm giving a presentation is that fishing is terrible. It does not lead to a Nature publication. It's not floating at the bottom of the pond or something. This is more and more and more common. And there's been lots of articles out there talking about what happens when you keep drudging the data and trying to find statistical significance, especially in kind of secondary data analysis. Like if there's a big data set that's been used for something else, you get your hands on it and you're trying to do a bunch of secondary data analysis, that's when you end up finding spurious associations. There was a really important article out about the relationship between thongs, flip-flops, and unintended pregnancy. So here's a table from that paper, and just to point out a couple important differences. If you prefer to wear thongs, you're more likely to have an unintended pregnancy. If you prefer Doritos over potato chips, that can lead to unintended pregnancy. And if you prefer yoga over running, again, better watch out. So if you don't learn anything today, you should learn that if your significant other or yourself wears thongs, likes Doritos and yoga, and wears contacts, watch out, because you may have an unintended pregnancy on your hands. Okay, but realistically, why is data mining so common? Well, 40 years ago when people were doing statistics by hand with an abacus, right, we couldn't do a bunch of statistical comparisons because they would take years. But now we have computers that can literally press a button and run everything for you without you really even thinking about it. And unfortunately, there's incentives in science to publish papers, right? Publication performance is linked to institutional funding. It's linked to career progression and salary increases. And actually, in some countries, they give financial rewards to their employees who publish in high-profile international journals. So you feel this pressure, whether it's financial or career motivated, to get out papers, right? Next point, low statistical power. A study by Dr. Button in 2013 found that the average power of neuroscience studies is around 20%. It's pretty low. But, despite clinical significance, we fail to detect statistical significance because our sample size is too small. So what ends up happening is it creates this sort of file drawer problem, right? There's a lot of studies out there that are likely from small sample sizes that aren't published because they failed to find a statistically significant difference, even though they may have found something clinically significant. It's really hard to get small sample sizes with non-significant results published. And why is this? Well, you can have low power because of many things. Obviously, if your sample size is small, you have low power. But you may have a very heterogeneous patient population. You could have a very rare outcome. You could have an uncommon exposure, or your outcome measure may not be well defined. All of these things will ultimately affect the power of your analysis. So I can't stress enough why, even if you're going to go do a retrospective chart review, you should probably do a quick power calculation. One, to figure out how many charts you need to review to find the difference that you want to detect. Sometimes we say that difference is the minimal, meaningful clinical difference, whether that be a one-day difference in length of stay, a 5% or 10% difference in mortality, whatever it may be. Also, what if you only need to review 200 charts instead of reviewing 500 charts, right? You may save yourself some time and energy if you do a power calculation ahead of time. And a lot of journals will require you to put in a power calculation to say that, hey, this is my hypothesis, this is what we wanted to study, and we made sure beforehand that we had enough power to study that. So to give you a quick illustration of the issues with power, I have a bunch of different sample sizes here. On the left-hand side, we're assuming equal numbers per group, just two arbitrary groups. We're looking at mortality. Here's my effect size, the absolute difference in mortality, and then power. So this is not changing. This is not changing. The only thing that's changing is my power. So again, it goes back to that, clinically meaningful difference. If 10% is an important difference, and I only have, 100 patients, I'm not going to have power to reject my null hypothesis. Again, but the clinical significance hasn't changed, and maybe no one will believe you with 100 people. But if you get 200 people, again, I don't have sufficient power to reject my null hypothesis. So I think what's important, again, is that you really have this trade-off between what's clinically significant and what's statistically significant. And hopefully you find both. But just knowing that something P is not less than 0.05 doesn't necessarily reject clinical significance. Number 3, overstating the results of an observational study. When you have an observational study or retrospective study, you cannot say that one variable caused the difference in another. This is not an experiment. You did not manipulate anything. You're just observing things. So the correct way of interpreting your results is to say that the two variables are associated or correlated. And again, don't forget that your significant results may be spurious. All right, reporting group means for paired data without reporting a within-pair change. So here's a paper, I think this was back in April, this came out, looking at neurocognitive changes associated with surgical resection of the left and right temporal lobe and gliomas. So here's their table 3. It's hard to interpret the results here. They found a significant effect of surgery, so that means that from preoperative to postoperative, there was a significant change in their Z-score related to learning and memory from their neurocognitive test. They found a significant effect of hemisphere, meaning that if your left temporal lobe was resected compared to your right, that would lead to a significant difference in your neurocognitive performance. And then they found an interaction, and that's what the interesting part is the interaction, which means that your change from preoperative to postoperative in terms of neurocognitive performance is affected by whether your left or right temporal lobe was taken out. So the problem is I don't know how to really think about that. I mean, I can see there was a big drop in this group, maybe about 1.5 Z-scores. Here, there was maybe about a 0.5 change, but it's really hard to wrap your head around, okay, what's the actual difference? What should they have done? They should have presented the average change in each group so that you can directly compare. Here was my expected memory performance decrease. Here was my expected memory performance decrease in the other group. So it's really hard to compare the relative change within each group without reporting that change. And so I think it's really important that we actually report those things out. And my last one, which I've already kind of been, alluding to this whole talk, is interpreting lack of statistical significance as no difference and equating statistical significance to clinical significance. Again, it's a red flag. when someone treats something statistically significant and clinically significant without really thinking whether it's relevant. Statistical significance simply rules out chance. Again, doesn't imply clinical significance. So I made up some data. We're looking at length of stay between patients that are clipped versus coiled. Again, wow, highly significant p-value, but look at the difference. The median length of stay is 5.1 days versus 4.9.
You didn't include all the readmissions.
No. So again, they're 5 days each. They're not different from each other. Just because they're statistically significant doesn't mean anything, right? But then I can look at their modified Rankin scale at discharge and maybe argue that a 2-point difference on the scale is clinically significant. Again, purely made up. So again, a p-value is a function of an effect size and the sample size. The larger the sample size, the smaller the p-value. Clinically important differences are found to be statistically significant just due to, insignificant due to low statistical power. So I give you this example without telling you the sample size. Treatment A, mortality is 50%. Treatment B, mortality is 30%. Would you favor treatment B just by looking at the mortality rate? Maybe. 50 per group, P is not less than 0.05. Here, same difference. 60 per group, now P is also less than 0.05. So the fact is, you don't change your clinical interpretation of this. The only thing that's happening is your p-value is changing. So again, the effect size and clinical significance stay the same, but the statistical significance changes. Okay, my last part of my talk. Let's talk about statistical considerations for non-randomized designs. So there's two major types of non-randomized designs. There's retrospective studies, where we look to identify our outcome measure ahead of time, like death, readmission, relapse, and then we go back and try to compare different exposures that may be associated with that outcome. And then we have prospective observational studies, where we look at patients by their exposure, like a certain treatment they got, and then we look forward to see what outcomes they developed. Again, prospective cohort studies are good when you can't randomize patients or you don't have the money to do something like that. So why do we do a retrospective study? Time is a factor. If it takes a long time for your outcome to happen, like remission or relapse or something like that, you may not have the time to wait to watch what happens to those people to observe your outcome. A lot of time you don't have any money, right? You can't enroll patients in a study and not pay them. You don't have clinical research staff. You don't have, any kind of money to do anything. So the easiest thing to do is a retrospective study. Again, your outcome is rare. You don't want to do a prospective study when your outcome is rare because you'll spend all this money and time and then you'll realize that only 5 people died. So why do you do a prospective study? Well, you have lots of time. Usually you have money. And your outcome is common, but your exposure is rare. So it's really important to identify people by their exposure up front. So again, for many studies, we can't randomize. And so our treatment groups may be very, very different on the onset. So what do we do? If your treatment groups aren't comparable before the start of the treatment, then they're not comparable in terms of their outcome measures due to the imbalances in their baseline characteristics. So any kind of treatment comparisons you make between those two groups may be invalid or lead to biased estimates. So in non-randomized designs, our treatment assignment is rarely, if ever, random. So patients are given treatment based on the severity of their condition and not based on the flip of a coin, right? A lot of times we think about this as confounding by indication. Patients that are sicker are going to get more aggressive therapy, and thus their outcomes associated with that therapy may actually look worse because they were given to sicker people. So does that mean that the treatment's bad? You have no idea. So I'm going to talk about an example of how to analyze data like this. We looked at patients that had spontaneous ICH, and we wanted to compare outcomes between patients that got an EVD versus those that did not get an EVD. So again, anecdotally, you're going to give someone an EVD when? Potentially they're sicker, or they're kind of in the middle of that group. Maybe if they're too sick, you don't bother. But if you look at this table, this was just some baseline characteristics of our patients that had an EVD versus that did not get an EVD. There's a lot of differences, right? the location of the ICH, they have a lower GCS score, they have higher ICH volume, they're more likely to have interventricular hemorrhage, and they have higher Graves scores at baseline. So in all practical purposes here, the EVD kids look, or say adults, look much sicker. So how can we compare the outcomes of patients that got EVDs compared to those that did not, when the patients that got EVDs appear sicker? So they're going to have higher mortality rates, right? So what methods can we use to control for these differences that allow us to make meaningful comparisons between the groups? So there's 3 common methods for adjusting for confounding covariates. Matching, right? You can find patients that are similar, okay? And sorry. You can find patients that are similar and put them...
Any Charlie Brown up there?
I'll use that one next time. So you can find patients that are similar and compare them. Harry Potter. Yeah. You can do a subclass stratification, which means that you identify subsets of patients and you perform the analysis in that subset. Or you do regression or covariate adjustment, which is typically the most common. So the question that we have is, what do you do when there are so many covariates that you need to adjust for? If you have a limited sample size, you can't put 5,000 variables in the model to attempt to balance your treatment groups. Matching is not practical because if I have to match 2 people on a bunch of different characteristics, I'm not going to be able to match anybody. With subclassification, again, as the number of covariates grows, the number of subclasses and subanalyses that you have to look at is exponentially growing and not possible. And with regression adjustment, you may have this issue of overfitting your model. Your sample size may be large and you may not have, or sorry, too small and not have enough power to model all your predictors. Which brings me to the whole point of my talk, or the last point, a propensity score. How many of you guys have ever heard of a propensity score? A couple people, okay, nice. So the idea with the propensity score is that you collect all these variables that are different between your 2 treatment groups and you put them in a model. And out of the model you get one single variable, a composite score or propensity score, that attempts to store all that information. This is gaining popularity. Propensity scores have been around since the 60s and 70s and done in a lot of different economic and consumer statistics. But it's really gaining some traction in the medical community. So PubMed search, you can see in 2006 there were only like 170 publications related to propensity score methodology. I did a quick PubMed search, and this year alone there's been almost 2,000. So people are using this. So how does a propensity score work? You take all the covariates of interest and you throw them in a model. You put a logistic regression model to predict treatment. We're not looking at outcome right now. We're just looking at trying to predict treatment assignment. Some magic happens in your logistic regression model, and out comes a propensity score. A propensity score is a conditional probability of receiving treatment A, like getting an EVD, rather than not giving an EVD, given a collection of observed covariates. So again, our EVD example, the propensity score represents the predicted probability of getting an EVD given the variables in the model. The purpose of this is to simultaneously balance as many of these covariate differences between the 2 treatment groups and reduce the bias. So again, we're using a statistical model to model the relationship between treatment membership and your covariates. It has nothing to do with the outcome right now. We use multiple logistic regression. Our outcome is treatment membership, and our predictor variables are variables that differ between the 2 groups. So there's been a lot of papers in the Red Journal that have actually used propensity scores. And when I just did a quick search, I found 65 publications in neurosurgery that have had the word propensity score somewhere in there. So if we go to our EVD paper. So these are all the variables that we threw into our propensity score to predict EVD utilization. And some of these are significant, some of these are not significant. The beauty of this is that there's really no concern with overfitting your models when you're doing propensity scores. If a variable is not significant, then it's not really going to contribute to the propensity score, and that's okay. So some people are always like, oh, well, why did you put gender in there? It wasn't significant. It doesn't matter. You can put really as many variables you want into your propensity score without running the risk of overfitting. So the propensity score is the predicted probability of treatment given your underlying covariates. So again, ours is the probability of getting an EVD given the patient's baseline characteristics. And how do I interpret the propensity score with two patients? So two patients with the same propensity score are equally likely to get an EVD given their baseline covariates. So it's like randomization after the fact, right? I have a bunch of patients in here that have a propensity score of 0.7. They all have a 70% chance of getting an EVD. Some of them got an EVD, some of them didn't. So it kind of makes you think of what a true randomized design is, right? Patients are equally likely to get a treatment. One gets it, one does not get it. So you can think of propensity score as like a randomization after the fact. Okay, well, what do we do with them, right? Okay, it's great we have a propensity score, but how do we use them in our analysis? So matching is probably one of the most common ways. And what you do is you match patients on their propensity score. So I find a patient that has a 10% chance of getting an EVD, but they didn't get one. And I match them to someone else that had the same probability of getting an EVD, but they actually got one. So it's almost like they were randomized, right? Same thing here and here. The problem is that patients that you can't match, they get thrown out of your analysis. So in a lot of times you reduce your sample size with matching. You can do a regression adjustment. This is where you predict your outcome like mortality using only the propensity score and your treatment variable. And the idea is that propensity score is one number, but it represents all that covariate imbalance. So you're adjusting your effective treatment with the propensity score, and so that will help balance out all those covariate differences. This is nice because you don't need to discard any observations.
Okay, what happens when you've collected 5 variables, but there's like a Wizard of Oz variable behind the curtain that you didn't collect?
I'll get to that. That's a problem. That's a problem. So stratification is when you basically break your data into different subsets based on propensity scores. And that's actually what we did for our EVD paper. So we broke it up into 3 different groups: patients that had a low likelihood of getting an EVD, patients that had a moderate likelihood, and patients that had a high likelihood. And again, there were patients within these groups that got EVDs and those that did not get EVDs. And you can see here that EVDs really, in this case, didn't matter in terms of outcome. You did see a moderate reduction in mortality in all of the groups, or the moderate and the low, but it wasn't statistically significant. So issues with propensity score estimation. How do you handle missing baseline covariates? When you use logistic regression, you have to have all the variables in the model, or they kick the patient out. So if your patients are missing a lot of variables at baseline, then they're not going to be, A, they're not going to get a propensity score, and B, maybe those variables are not good to be put in your propensity score to begin with if a lot of patients are missing them. How do you decide what covariates to include? And again, which method should you use? Matching, stratification, regression? Propensity scores can only adjust for observed confounding covariates, not for unobserved ones, like Dr. Gross mentioned. If there's variables that are important that you haven't collected that could seriously be explaining, why treatment membership was given, then your estimates may be biased because you didn't collect the important variables you needed to collect. So that's important. You have to have clinically meaningful variables in order to do a propensity score. And then the caveat is that subjects with similar propensity scores are not guaranteed to have the same distribution of underlying covariates. So just because you have a propensity score of 0.7 doesn't mean that you have all the same covariates as if you were to match people. So you could have like an 80-year-old woman who's a chain smoker, an alcoholic, she's underweight, high risk for certain outcomes, be matched to, a middle-aged 40-year-old man who's overweight. They could have the same predicted probability of treatment, but yet they look very, very different. So final thoughts about propensity scores. They're a useful technique for adjusting for confounding, and that uses a single variable to simultaneously balance many covariates. They're not the only way of adjusting for covariates. You can always use multiple variable regression to model those covariates along with your treatment of interest. Again, randomized trials are considered the highest level of evidence, and so propensity scores lack that discipline of rigor that randomized trials have, and they're not a substitute for randomized trials. So conclusions for my talk today. Statistics are complicated, right? Consulting with a statistician is a good idea. Common statistical mistakes can be avoided if you just take the time to look at your data prior to doing any analysis. Treatment comparisons and non-randomized designs can lead to biased results without proper adjustment for differences between groups. And propensity scores are a useful tool for overcoming limitations in non-randomized studies. Thanks.
Courtney, that's terrific. Can an analysis after the study's been done go dig into this question of an unknown covariate there that you didn't measure but may have affected your treatment? So in other words, let's say you had you ran the study and you had two groups that were exactly matched, but clearly there were variables in there that were at loggerheads, like the thin lady who smoked and the obese guy who was whatever. Could that trigger the investigator to say, wait a minute, these two seem to react the same way in treatment outcomes, but they were sufficiently different in their variables, even though they had the same propensities. So like kind of a forensic analysis.
Yeah, it's hard to do that. I think a lot of studies are now like pushing you to, and you're like whether you're writing a grant, is to really push you to do heterogeneity of treatment effects as part of your analysis plan, meaning that you say up front, like you're going to look at how treatment works in a lot of different subgroups, because you may get this average treatment effect that looks to be significant, but in certain patient populations and subgroups, it may not be effective, or it could show the exact opposite effect. But depending on how rare that subpopulation is, they may not be contributing to the overall main effect of treatment. I mean, again, it goes back, you have to have the variables there. You can hypothesize what may have caused that, what underlying, variables potentially could explain this, but you got to collect it. I mean, that's, you can't really, you can hypothesize, but you can't make any logical analyses if you don't have the data to support it. So, a lot of post-secondary data analysis of large studies suffers from this. The data has already been collected from the onset, and here you are trying to do a secondary data analysis, and you may not have the right variables to adjust for in your analysis. So, hopefully, the reviewers will pick up on that when they're looking at your proposal to do the secondary data analysis, but it's not guaranteed.
Two comments. One is all of this was about clinical studies, and I think people almost tacitly assume that preclinical studies, basic science studies, are appropriately statistically treated, when in fact they're even
the worst.
They're
the worst.
I mean, we constantly do studies where we, do 4 animals, take a look, say, oh, okay, let me just add a couple more, see if it works out until you hit that 0.05 level.
Yeah.
And they're just this year has started a supplement to the T32 grants here, where a course is being offered for the basic science PhD students in statistical techniques.
Yeah, I give a stats for rats talk to our basic science researchers to kind of talk about some of the issues. The problem is that the medical journals that these articles are getting published in are not holding them to the same scientific rigor as, say, clinical research journals, partially because most basic science researchers do their own statistics. They're all using t-tests incorrectly, so they don't see a problem with it, and the journals don't see a problem with it either. And again, there's a lot of issues that are, in basic science because you have such small numbers, but there are ways to overcome it, and you can still find statistical significance despite, really small numbers.
And that leads to the second point, which is, that once you get it in, it's written in stone, okay? And then that's it. I mean, people rarely dig down into a paper to see about the conclusions and then go to the trouble of writing a letter to the editor, back and forth. So and you showed a couple of particularly egregious examples from the Red Journal of bad statistics. And in the Red Journal process, the reviewers check off, should a biostatistical statistician take a look? Yes, yes, no. And that assumes that the reviewers who are ignorant of statistics know when a study should be evaluated by a statistician. And clearly they get through. So should all journal articles be subjected to a biostatistical review?
I think anything other than a case series should be.
I think so. When I started with the Red Journal, I instituted a biostatistical review system, and Courtney being one of our staple of biostatistical reviewers, and take the decision to make every paper that is, that claims to have deductions based on statistics. Now you can have a clinical paper that presents material, but the main claim to fame of the paper is not the statistical rigor or maybe a new technique or certain outcomes or whatever it is. Whatever. No, case series. But the claim of the paper is not, look at it as, we created this phenomenal model and here's the deduction that is rigorously based on statistics. So that allows us to use that threshold. They may report statistics.
But that's not what presently
the paper is
exists
about.
right now. They don't automatically, if they report a statistical test, they don't automatically.
No, just because you report a statistical test like
It's
a
up to
mean
the
or a
review,
rate,
it's up to the editor.
doesn't mean that it is. But if the main claim of the paper rests on bedrock of statistical gymnastics, then that's going to be reviewed by a statistician. I make sense.
So I got one from Dr. Gross the other day. So yeah.
We've had a couple almost slip by.
Well, there's always going to, there are no perfect papers, even in the best journals. There's always going to be areas you find, but and that's just the case. This guy, I don't know if you've read Ionides. Do you know who he is, Courtney? So Ionides is at Stanford. I don't know exactly what his particular specialty area is to start with. But anyway, he's one of the most published and cited people, all of the biomedical literature. He's like near Stanford or something, in that league. And he's written some seminal papers on the problems in medical literature. And I mean, he says that most, if not nearly all, of papers in the medical literature are flat out unbelievable and are wrong. The deductions are wrong and so on. For the kinds of reasons that you stated.
Yeah. I think it's important that anytime you're evaluating research, you're looking for reproducibility. So if several studies come out and kind of find the same thing, then you should think to yourself, well, this is probably pretty believable, right? Because it's been reproduced. So sometime the first time something comes out, take it at face value until somebody reproduces it.
So, you talk about randomized studies, so I think that's probably a whole other talk you could give to us about the appropriate use of randomized studies. So that's exactly true what you just said, that it's actually, I can never find the reference to find out where this is written, but I know I saw it somewhere, that multiple studies done, non-randomized, non-controlled studies done in different times in different places that show the same result is supports a more powerful deduction than a single randomized clinical trial.
And that's true because a randomized trial is like in a petri dish, right? Everything is going as perfectly as possible. It's not real life practice, and so if, again, like a meta-analysis that comes out and synthesizes a lot of studies and shows a significant finding, that to me and sometimes is a higher value than just one randomized trial.
But we approve things for patient treatments based on a single randomized clinical trial.
Oh, yeah.
That's what the FDA does.
Oh, yeah, all the time.
And we reject studies that probably suffer from some of the things you said but have high clinical significance on the basis that they hit 0.04.
Right.
So we talked about this a while ago in my own field of stroke and intravascular. It's important, I think, for students, residents, certainly faculty and conductors to know that every time you publish a paper, it's with an agenda. And when you're reading that paper as a naive person just interested in the field, you should understand that there's always some subtext to it. So in the field of stroke, there are these national databases kept with the guidelines and whatnot that, as you say, which I think is a great example, a small effect in an enormous sample size always gives you statistical power.
Right.
And then in a multivariate analysis, it's 8 times, 10 times, 20 times more likely that someone's going to have a better outcome for every, let's say, with acute stroke treatment, for every 5 minutes of treatment. But actually, what is the magnitude of that effect? It could be absolutely trivial. However, because it's in a large database, then it's statistically meaningful, but clinically irrelevant. And I think that it's very important to get educated on what those analyses mean before you go to the next leap. It's huge. And these papers are published in New England Journal, JAMA, Lancet, So just because you're reading an article in those journals, Red Journal, doesn't necessarily mean that the take-home messages are actually clinically meaningful, even if they're statistically significant.
Because remember that all reviewers are not created equal. And whether they're biostatistical reviewers or content reviewers, they're not all created equal. So just because the reviewer looked at the paper and said, this passed the sniff test, doesn't mean it does. I mean, that's why there's stuff in the literature that's subject to criticism after publication, even from the very best.
Thank you.
Thanks.
Courtney. Thank you.